This mini lecture is about phases of matter and intermolecular forces. Now I'm going to click here for an introduction, and we can see that this will show us what phases of matter will look like. Now if we're looking at solids pretty much look like this. They're just packed together and they're not really moving very much. I mean, you might get a little bit of vibration in the solid. It just sort of hovers up and down just a little bit. And of course at absolute zero that motion would stop absolutely completely and would be completely still. But in most solids, of course, at room temperature, you're going to get a little bit of this vibration going on. There we go. And that's all you're going to see. Of course, when it melts, it will go everywhere and lose its structure completely, and it becomes what amounts to a liquid. Now, this representation of a liquid is not entirely accurate. I would say it's more accurate to say that these liquid molecules are all still touching each other, but the movement would be all around. So this particular little molecule here would move over here and here and here and here, and this one would move over here and here and here. So I'd really like to see more movement of all of the individual molecules, but the important point about a liquid is that those molecules will all remain touching, and that's very important when we talk about intermolecular forces. Now, boiling, what's going to happen is that all of these molecules will separate. They will no longer be touching. And that's the important difference between a gas and a liquid. Liquids have all the molecules touching. Gases have all of the molecules all apart. With intermolecular forces, there are three that we talk about: van der Waal, we talk about dipole-dipole, and we talk about hydrogen bonding. The weakest of these three forces is the van der Waal forces, and we most often see these with hydrocarbons. Hydrocarbons are so named because they are just made up of hydrogen and carbon. The important point about this particular intermolecular force is that it is the result of a temporary dipole. So what I've tried to represent here is a circle around the carbon atoms that represents an electron cloud, or the electrons in the CH bonds essentially. And what's going to happen is those electrons are going to move from one side to the other. And the double arrow here is indicating that that's what's happening, is it's moving to one side and then it's moving back to a situation where there is no polarity, or it can move the other way. So you can see this illustrated in this diagram here. Alright, so this is a really nice interpretation of van der Waal forces. You can see what's going on is the electrons are moving from one side to the other. It's a very temporary type situation on the dipole. And this is what we're seeing. And that's what this arrow here is showing. It's showing the difference in the electron distribution going from one side of the molecule to the other. But the important point to note is that it's transitory and temporary. Alright, so what can happen is these temporary dipoles can line up from positive to negative, and this can have a degree of holding these molecules together in liquid state, just having the molecules remaining in a touching fashion. These forces are not particularly strong, but they're strong enough to keep a lot of these hydrocarbons in liquid form, provided there are other conditions satisfied, which we'll talk about a little bit later. The next strongest force is dipole-dipole forces. As you can see, those are 10 times stronger than van der Waal. Now that's because the dipole here, instead of being temporary, is now permanent. and is as a result of an electronegativity difference between carbon and some kind of atom attached to it. Usually another non-metal like a fluorine, bromine, chlorine, iodine, that is a halogen, or a nitrogen, oxygen, sulfur. And there's some of the other nonmetals as well, but those are the most common ones. So these are permanent dipoles, and because the dipoles are permanent rather than transitory, these tend to be 10 times stronger than the van der Waals forces we were just talking about. And this page will show an animation of that as well. You can see this here. Because these dipoles are permanent, you can see how they might be inclined to line up from positive to negative and engage in activities that will keep these molecules pretty much stuck together in the liquid phase. The strongest intermolecular force we're going to talk about is the hydrogen bonding force. This is 10 times the dipole-dipole force. It's really just a special case of dipole-dipole, but it's what we observe between OH, NH and FH kinds of bonds. Because the hydrogen atom is so small, you can see that that's going to result in a smaller distance between the hydrogen and the atom that it's attracted to, which is going to be, in this case, an oxygen in another molecule. So this distance between the H and the O will be fairly small, resulting in a fairly strong intermolecular bond between these two. As I said, these are 10 times stronger than dipole-dipole forces, which makes them 100 times stronger than van der Waals type forces.